Now that we've gone through talking about centroids and that idea of where the center of a body is and how this was similar to our distributed loads and how that concept applies to distributed loads, now we're going to look at centroids of composite bodies. And this is, again, a similar idea to what we did with our distributed loads, where we had, say, some distributed load that was on a beam, and we said, okay, this looks kind of familiar, right? We can see that we can split this guy up into a rectangle and a triangle and just take those areas, right? Integral is just the area under the curve. So our distributed loads, we're just doing these integrals where we're finding these two separate areas, and we were calling that good. That's our distributed load, calculating that way. This is going to be the exact same idea, where we're going to have shapes that we're already familiar with or that we can easily work with to get our areas and find the centroid of the individual shapes and then bring those together in our equations. So now the equations that we're going to be working with aren't integrals, but instead are summations. So very similarly, our x bar, our x locational centroid, is going to be the summation of our x tilde times a over the summation of the areas that we have. And same with our y bar. So again, these are the same equations that we had. Just now, instead of those integrals, they're going to be summations. Just kind of a different way of writing it, a different way of thinking about it in your brain. So in this centroid analysis, you might be given some kind of shape that looks like this, something that looks like you can break it down into simpler shapes. I want you to pause the video and see how many shapes you can break this out into. And I know that seems like a really simple task, but know that there's more than one right answer here, right? I was able to come up with 3 different ways that you could break this out into shapes. So the first grouping of shapes, and the one that might be most obvious to you, is delineating right along lines of what we see. So saying that we have 1 by 1 square, and then I see I have this rectangle here. This is a 3 by 2 rectangle. And then finally, I have a 3 by 3 triangle. But we can also account for the blank spaces. We can add in blank space shapes and use those as subtractions. So what we could do is we could say, okay, I'm going to do this whole thing as one rectangle and find the centroid of that rectangle, right? Break it out into that shape. So here, taking the whole rectangle that I see, which is a 3 by 6, and then subtracting out these blank spaces, right? So I have these voids, we call them. So here I have a void that is 2 by 1, and then that triangular void up there, again, 3 by 3. And these voids, instead of adding them to my things, I'll be subtracting them out. I could take the centroid of the big thing and then subtract out the centroids of the little things. Still works in my summation. I'm still adding everything together. But now that I'm adding nothing, I'm adding these voids, these are getting subtracted out. So this is another way that I could set this up. And I kind of make that clear for myself in my mind when I write these out. I shade in the areas that are actually existing, and then the voids, I can either put a little note next to it that says void, or I can leave them blank, right? No shading in the interior, just as a note to myself that, okay, I've got 3 shapes, one of them is an actual shape, and then 2 of them are getting subtracted out. But this isn't the only way you can use voids in this. You could also, combine those ideas. So I could say, maybe I want to do this entire square, this 3 by 3 square as a whole, the 3 by 3, and just subtract out this part. Right, so still leaving that 2 by 1 as a void, but now instead adding my triangle. Adding this 3 by 3 triangle that's over here. So there are multiple ways that you can break down these shapes to get your centroids. All of these should get you the exact same answer, just a matter of whether you're adding or subtracting things. And it can really be helpful, especially if you have something like a hole in the middle of your shape, right? So maybe you've got something with a hole punched through it. Maybe there's something with a, half circle sitting at the bottom. You have some kind of mouse hole at the bottom of your door and you need to find the centroid of your door. Some kind of quarter circle hole. Things that are in the interior that you really have to take a void for. In this case, none of these have to be done as voids, but in some cases it might be easy to subtract something out that's not there. Let's take a look at an example. Oh look, for our example, we're actually going to take this exact same shape that we just talked about, go ahead and I'm going to show you a tabular method, so a way to use a table to kind of make these centroid calculations a little easier for yourself, because we've kind of got a lot going on in this equation, right? A summation, you get lots and lots of parts, and usually the easiest way to sum something is, well, we plug it into Excel, right? So we're going to make ourselves a table so that we can just add everything down the rows and then punch those in as our very last things. So in our summation equations here, our x bar and our y bar are what we're looking for. So this is the summation of x tilde over x tilde times a, times the area over the summation of the area. And y bar is the same, but with y tilde times a over a. Both of those summations. So what we're going to do is build a table that contains the area, then the x centroid, that x tilde being the centroid of every single one of our different shapes, and then the x times a. So that way we can just sum down the columns. So first things first, let's write out the shapes that I'm going to be using. So I'm going to do this example using one of the voids, and I know this might not be as intuitive to you, but just to kind of get a sense of how we would approach a void in this situation. So I'm going to go ahead and make my shapes. This will be my first shape in red here. One will be a shaded in 3 by 3 square. So my shape 1 is the full area of this 3 by 3 square. My shape number 2, I will go ahead and have as the void. So this will be subtracted out. Shape 2 is the 2 by 1 void. And then finally, my shape 3, I'm going to do just the full triangle. Not have any more voids in here. Just the 3 by 3 right triangle. Excellent. So I'm going to use each one of these shapes and build them into my table. So I can go ahead and analyze them for their centroid and their area and everything as I'm going along, right? Let's move these up so that I can build my table. Oops. All right, take you, put you up here, and I'm going to do my basic table setup. So again, what I want is I want the shape, I want my area, I want my x and y centroids, and then those multiplications, right? The x times the a and the y times the a. So in this, I'm going to have shape. Build a big long table here. Shape, a for area, my x tilde for each shape, a times x tilde, my y tilde for each shape, and then y times a. So those are all of the components that I'm going to need to plug in to my centroid equations. So let's go ahead and do shape 1 first. So I'm looking at shape 1 over here. The area of shape 1 is pretty obvious to us, right? It's a square that is 3 tall and 3 wide. It is going to be 9, right? 3 times 3, simple as you can get, just the area of a square, 9. Boom, put that down into my table. Next I have my x tilde, and this is the centroid just of the shape, but it remains in the context of the diagram that it was drawn in. So my x centroid, while you might think, okay, it's going to be halfway through, so it's at 1.5, but we have to keep in mind the context of where it sits in the xy axis that was given to us. So actually, the centroid is somewhere in here. This is not drawn to scale, but it's somewhere in here. And we know that it's actually going to be a negative 1.5, right? Since this is 3 and it occurs halfway, it's going to be a negative 1.5 from the x direction, right? Negative 1.5. So every time we're looking at these, we need to keep in mind how they're offset from the x and y axes, because they may not be touching either, right? So if this square, had, say, another square to the left of it, then it would be 3 plus, and then whatever the centroid of that shape is. So just bear in mind that everything is in relation to what was given to us, not necessarily in relation to the shape itself. Okay, so we have A, we have our x tilde. So this AX column is literally just multiplying those two together. So my 9 times my negative 1.5 gives me negative 13.5. Easy enough. Then I'll do my y components and that multiplication. So my y centroid here is going to be, again, halfway up through the square, and all of my y is positive, so it's just 1.5. 1.5 is where my y centroid is of that shape, and my a times y tilde is going to be a positive 13.5 this time. So that's all it is finding these numbers for each individual shape before we sum them down. Let's go ahead and do our next shape. Shape 2. Now this is a void. And the key thing to know with a void is that a void gives you negative area. So a void gives you equals negative area. So whatever area I'm put in this A box has to be negative, and that negative carries through in the multiplication. That's how it gets the math to work out correctly. So my area of my void is 2 by 1, so it's just 2, right? 2 times 1 is 2. So a negative 2. Negative 2 in my area. Now I have my x tilde. And here we'll notice that my x, my centroid of this guy, is right about in here. And so normally we would think, again, okay, this is, 1/2, right? Half of 1 is half. So you might think, okay, well, is it negative 1/2? But it's actually offset by this entire distance here before we get to this 1/2 that gets us to the centroid. So it'll be 2 plus that 1/2, right? So this distance here, this distance is 2 feet. And then this distance from that 2-foot edge to the centroid is 1/2. So it's 2.5, but it's in the negative x direction. So that is negative 2.5. And of course, that means that when we multiply through, our a times x tilde is going to be a positive, right? Negative 2 times negative 2.5 gives us positive 5. And that's okay. The math is still going to work out just how we expect because we've done all of our signs correctly. So now we do our y bar, and this is the exact same situation, right? You might think that it's 1 because 1 falls halfway through the 2, but this 1 is again floating up above this 1 foot square, whoops, this 1 foot square right here. So it'll be 1 plus this 1 to the centroid. 1 to get up to where we are, 1 to get, once we're in the shape, to the centroid, which is 2. 1 plus 1 is 2. And then multiplying across, our a times y tilde is -2 times 2 is -4. All right, that just leaves us with one last guy, one last shape to do here. And that is our triangle. So now, you know, his area is a little more complicated, and he's not just a square or rectangle. He's going to be 1/2 base times height. So 1/2 3 times 3 is going to be 4.5. And again, his is positive because we are looking at him as his full area. So we've got that 4.5. We know the centroid of a triangle lies 1/3 in from the tallest side. So 1/3 in here is going to be at 1. Easy enough, and it's in the positive x direction, and there's nothing offsetting it from the axis, so just a 1. And then a times x, super easy, 1 times 4.5 is 4.5. And then this is an even easier shape than our rectangles, really, because we do our y tilde, and it's the exact same, right? 1/3 of the way in from the tallest side is, again, 1. And then 1 times 4.5 is 4.5. So this is the complete table that we're going to use. And if you'll recall our centroid equations, move my shapes out of the way. Our centroid equations, we needed for x bar the summation of x tilde a over the summation of a. And for our y bar, we needed summation of y tilde a over summation of a. So what we're going to do is just add these down their columns. Right, so all I need are my a column, my ax column, and my ay column, because these are the guys that are actually getting plugged into those centroid equations. So I add them on down. Right, 9 minus 2 plus 4.5 is going to give me 11.5. My ax, -13.5 plus 5 plus 4.5 gives me -4. And then this 13.5 plus -4 plus 4.5 gives me 14. So I can pop these puppies into my equation. And I have my -4 over 11.5, my x bar, my x centroid. And then I can plug into my y, and that's going to be 14 over 11.5, so that I get my final answers of x bar, my x centroid, is -0.35 feet. And then my y bar, punch that into my calculator, and I get 1.2 feet. Before we move on, we always do a sanity check. Does this make sense? And the answer is, yeah, this kind of makes sense, right? We kind of expect that those chunky, blocky sides might skew this to the left-hand side a little bit more, right? It makes sense that our centroid, our x centroid, is skewed a little bit to the left of the axis. We expected it to be somewhere near here, right? Somewhere near the y-axis, but it's kind of balanced on both sides, but skews a little bit more on the negative x side. And then, of course, with a y bar, a y centroid of 1.2 feet, that totally makes sense. We can definitely see that making sense. You know, having a y centroid somewhere in here, not too far up, it's going to be a positive y. So doing just a quick sanity check, we're like, yeah, these numbers make sense, and even if they aren't correct, they're at least in the correct ballpark, right? They're not floating out in space somewhere weird. Everything is kind of where we expect it. So when you have these composite bodies, my main tips would be break them out into your shapes, then build a table so you can make these summations as easy as possible for yourself, and then of course do a sanity check. Now also keep in mind that these centroid equations aren't just for your areas, right? They can also be applied to volumes, masses, and weights, right? Your forces. Because center of gravity is really a very big thing that we care about. That would be the most important use in real life of all of this centroid stuff that we're doing. So we want to get some practice in with some other types of problems. So in this example, from a 2D space to a 3D space, where now we want to locate the centroid x bar, y bar, and z bar for this 3D set of blocks here. So we're going to apply the exact same equations, the exact same process. The only difference is that we're working with volumes instead of area. So our equations now, our x bar is the summation of our x centroid, our x tilde for each shape. Whoops, now it's times a. No, times v. Times v, our volume, over the summation of volumes. And then this tracks for our y and our z bar even, right? So nothing really new, just a different application. Same process. So we're going to do the exact same thing, break it out into shapes, make a table, and do a summation. The only difference is our table's just a little bit bigger because we've got this z-bar thing going on. So in this case, it's going to be a lot easier to not use a void, right? If we look at it and say, what are the simplest shapes that I can pull out of this thing? I can see a box in the back, right? This full box back here. Not to scale this drawing, but it is 6 feet by 2 feet by 2 plus 5 is 7 feet. So this is one box that I have. And then the other box that I have is this rectangle up here. Right, so here's shape number 2. And not exactly to scale, but we know that it is 3 by 2 by a depth of 4. So you'll notice that my orange box, I didn't include the part that was sticking into it, right? I'm gonna have one flat shape, one complete square shape, and then that guy sticking off of it is its own separate square shape, or rectangular prism, I guess if you want to be technical about it. But they're their own shapes. So I'll call this shape 2, so the guy I did is shape 1. So easy enough. It'll be a little bit shorter of a table, but I can still use my table, and I can go ahead and do my shape, volume, x, y, z, and then x times v, y times v, z times v for my table. So, boy, that's going to be a long table. Hope we can sit everybody at it. Shape. You know what? Maybe I don't write the word shape so big. Maybe let's just get rid of that. Alright, let's just make as much room as we can here. Alright, scoot that way off to the side. I have a volume. I have x. I have x times the volume. I have y. I have y times the volume. Oh, there we go. I've got enough room. Z. I've got enough room. Z times the volume. And I'll do my number 1 shape first. So my volume, again, is just going to be this, cubic type thing, this rectangular prism. So 6 times 2 times 7 is going to be 84. And this is feet, but I really don't have enough room on my screen to be writing out all my units, so I'm just going to know that it's feet cubed. Right, this thing is cubic feet for my volume. All of my units are going to work out in the end because I know that I'm going to end up with centroid locations that are all in feet, right? Nothing should be in feet squared or anything. So let's look at what my x-centroid for this guy is. So coming off of the x-axis, this distance here is 2 feet, and it is directly attached to that zy plane. So half of 2 is 1. So my x is just 1, right? That is the centroid location for this guy here. An x location of 1, a y location of, let's see, half of 7 is going to be 3.5. And a z location of halfway up from 6 is 3. So you may also find it simpler to just go through and write out your centroids first and then plug them into your table. Totally up to you, whatever way makes the most sense to you as you're setting these up. And you don't even have to use this table method that I'm showing you. You can just write out every single component and multiply it yourself within the equations. That's totally okay. You can do whatever way makes the most sense to you. The tabular version, this table is really popular just because it's very easy to see everything you need and see if you've missed something. When you're writing things out in an equation, it's easy to get lost, it can get very messy, but the table makes things very clear. So I like to use the table. It's up to you. Anyway, I've got all my centroids. I'm going to multiply them out. So 84 times 1, that's 84. 3.5 times 84, I don't know. I'll plug it in my calculator, and I get 294. And then 3 times 84 for my ZV gives me, gives me 252. All right, same song, play it again. For shape number 2. And I'll myself some space here though. Draw my line. All right. So my volume for my orange shape here is 3 by 2 by 4. So this little guy is, or has a volume, I should say, of 24. 3 times 2 times 4, 24. Easy enough. Now here's the part where it gets a little more complicated, is that you have to remember that this block is offset from the ZY plane, right? So always just remember that when you're not touching the origin there, when your shape isn't touching your origin, you've got to add any shapes that came before it. So this distance here between this block and this block is the 2. So we're going to say 2 plus, and then whatever the centroid distance is, which in this case it's halfway through 4. So it's going to be 2 plus 2 to get to where the centroid is sitting in the XYZ coordinate system. 2 plus 2 is 4, so this centroid is 4. Then next I have my Y coordinate, and since this is pressed up against the x-axis, it's just going to be halfway through my 2, so my Y centroid is 1. And then finally my Z, which again is flat up against the thing here. So halfway through my 3 here, it's going to be 1.5. I've got all my centroids listed out, just multiply out the volumes across, and I have 24 times 4 is 96. 24 times 1 is 24, and 24 times 1.5 is 36. Boom. That's it. My only 2 shapes. So now I just need to plug and chug. I mean, add them down the columns, plug them into my centroid equations. So again, the guys that I care about are my, are my volumes, and then my volumes times each component. So I've got 84 plus 24 if I sum down the volume column. So I'm going to put a summation here just to keep that in my mind. I've got 108. Here, x times v, I've got 180. If I add those down, 294 plus 24 is 318. And then my zv, 252 plus 36 is 288. So now I've got all those numbers, just plug them in so they'll spit out my answers, right? My x bar is going to be 180 over 108, or 1.67 feet. So there's an answer. My y bar is 318 over 108, which when I plug into my calculator gives me 2.94 feet. My y bar centroid, and my z bar is 288 over 108, which is going to give me 2.67 is my z centroid, 2.67 feet. So that's all I've got to do, right? Find those centroids. I can do a quick little sanity check and just say, okay, does 1.67 make sense for x bar? And the answer is, yeah, it really does, because, I mean, our x goes out by 2 and then another 4 feet, but most of the mass, most of this thing is sitting way back next to the zy plane. So it makes total sense that our x should be a little less than 2. And so then we can sanity check, our y bar, just about 3 makes sense. And we say, yeah, it kind of makes sense. Our y bar being about 3, and our z bar being also close to 3, 2.67. Our shapes are all, our z bars go to 3 and 6. All of these check out, all of these make sense. They all kind of fit within the shape. So if we were getting, negative numbers, for example, then we would want to say, whoa, whoa, where did we get those? But in this case, we're just like, it's probably pretty close. So we move on with our lives. To our next example. So for our last example, we're going to be looking at a little more of a real world type of situation. Is where we have this shop floor, there are a bunch of really heavy objects on it, and we want to locate the center of gravity on this shop floor, which, could be very useful, very practical for us as engineers, because maybe the shop floor is overloaded, maybe the center of gravity is in the wrong place for the loading of the beams and hoists and everything that is underneath. Maybe the foundation isn't enough to support this. Maybe we want to add in another object, and we want to know what would be a good placement for this so that our floor doesn't cave in, if we're on a basement or on the 14th floor of a building or something. So in this case, we have 4 of our heaviest objects on the floor, and we have locations for those on this X, Y, Z grid that they give us. So to find the center of gravity, again, very same process, right? All we're going to do is we're going to take those centroid equations, x bar and y bar, and now those summations are going to be for the weight of the objects. So the centroidal locations of those objects times the weight, all over the weight, total weight in the room. Now you'll notice that even though they gave us an XYZ plane here, we don't actually need the Z plane. Yes, the center of gravities do sit up at different locations, but what we're interested in is the center of gravity of the shop floor, right? So this is just in the XY plane. It doesn't really make sense for us to have a center of gravity floating up in the air when what we're interested in is what's happening on the floor. So for this, all we're going to look at is the X and Y bar centroids, right? X and Y bar. So to start this, we'll start it just like we start every other problem, by setting up our table. And this one's even easier because we don't need to delineate shapes. They already give us what all of our shapes are. They give us names even. We call them G1, G2, G3, G4. So I'll go ahead and set up my table here. That might be a little bit too low. I might need to move that up. But we'll stick with that for now. So our G1, G2, G3, and G4. I was wrong. I'm going to move it up right now. Our X bar and Y bar can come hang out later. All right. So I want to put my shapes in there, and then again, now instead of my areas or volumes, I'm putting in a weight. So I'm going to have my weight of every object, the x bar, value of the centroid, which also very handily is already given to us. Not much calculation is going to need to be done on our part. It's more of just locating those, making sure that we can properly locate these centroids. So let's do that first. G1, our G1 object has a weight of 450 pounds. 450 pounds. And off from the X, from our centroid there, going in the X direction, we can see that it's off by 6 feet. So our X bar is 6. And if we want, we can really just travel down the X line and just go ahead and capture all of these as we walk down, because we're just going to be adding these numbers together. Right, so from our 6 feet, the next one out is 12 feet, and that's G2. So the 6 plus the 12 at our G2 is going to give us 18. These are a little bit too close together. Give myself some more bars. There we go. All right. We can walk it on down to G3 is another 8 feet out, so I can add on those 8 feet. That gives me 26. And then G4 is the farthest one out in the X direction, plus 4 feet added onto that is 30. And I can go ahead and look at my Y's as well. So my G1 is out 7 feet. And then these are not as additive, so I can just kind of look down the line. My 7, well, for my G2, it is my 7 plus my 9. 7 plus 9 feet there is going to give me 16. And look on down the line. That green thing is G3, so it is 3 feet out from the x-axis. And then my G4 is another 5 feet out from that for a total of 8 feet. Then I can finish writing in my weights. I didn't write those in, so my G2 is 1500, G3 is 600, and my G4 is 280. Now it's just a matter of multiplying those out, multiplying across in my table, and then doing the summation. So my 450 times 6 gives me 2700. 1500 times 18 is 27,000. 600 times 26, 15600. And 280 times 30. Close this off. There we go. Is 8,400. Right? All I'm doing is multiplying these across, punching into my calculator. So my next one, my weight times y bar, 450 times 7, 3150. 1500 times 16 is 24,000. 600 times 3, 1800. And 280 times 8 is 2240. Do my summations, add up the things that I care about that end up in my equations. So adding up my W column to get my sum of W's is going to be 2830. The sum of X times W, this column is 53700. And then my final column, 31190. Okay, simple enough. Final step, just plug them into our equation. Go ahead and delete my table. All I need really are those summations at the bottom. So I can plug in my x bar. Summation of x's times w over w, which is our, that was the 50,000 number, over 2830. So x bar is 19 feet, right about. Probably a little bit of rounding there, but right about 19 feet. My Y bar, that was my 30,000 number. 31190 over the 2830. But my Y bar is right around 11 feet. Plugging and chugging right into our calculator. And then we do a sanity check. Do those numbers make sense? And we can see that the shop floor is about a little longer than 16 in the Y direction. And we know it's up to 30 in the X direction. So 19 and 11 strikes you pretty close to the center of the floor. So we see that the answer kind of makes sense, and we say, all right, good to me.